A core design choice in modern AI systems determines how they read and process information, and that choice is starting to show clear limits. Most people compare chatbots based on answers, but the deeper issue is the engine underneath them. The architecture behind systems from OpenAI, Google, and others is largely the same. That architecture is called the Transformer, and it has powered nearly every major advance in AI since 2017. The important point is not that transformers are failing today, but that their growth is slowing in a measurable way. Engineers are now seeing costs rise faster than capability, which signals a structural limit, not a temporary slowdown. The transformer architecture works by breaking text into small pieces called tokens, and then comparing each token to every other token in the sequence. This comparison process is called attention, and it allows the model to understand relationships between words. For example, when reading a sentence, the system can connect a pronoun to the correct subject, even if they are far apart. That is why transformers handle language so well. The process runs in parallel across many tokens, which is why these models scale efficiently at first. Hardware from companies like NVIDIA is optimized to handle this parallel workload, allowing fast training and inference. The success of transformers comes from how well they scale during early growth. When engineers increased model size and training data, performance improved in a predictable way. Systems like GPT-3 and GPT-4 followed this pattern closely and showed steady gains in reasoning and language quality. Each increase in compute produced better results, which encouraged even larger training runs. Large data centers were built to support this process, and the results justified the cost for several years. The pattern looked stable and reliable, which is why nearly every major AI company adopted the same approach. Please subscribe. The core limitation appears in the way attention is calculated as inputs grow larger. Each token must be compared with every other token, which creates a rapidly increasing number of operations. If the input length increases by a factor of 10, the number of comparisons increases by a factor of 100. This is called quadratic scaling, and it becomes expensive very quickly. The system must store and process a large matrix of relationships for every step, which consumes both memory and compute. This behavior is built into the design and cannot be avoided without changing the architecture. The scaling wall becomes visible when engineers try to extend context length or improve performance beyond what current models can handle. Training runs become extremely expensive, and each improvement requires disproportionately more resources. The cost is not only financial but also physical, including power consumption and hardware limits. At some point, adding more GPUs does not produce meaningful gains because the system spends more effort managing attention calculations than actually improving understanding. This creates diminishing returns, where progress slows despite increased investment. Engineers begin to question whether the architecture itself is the bottleneck. Hardware expansion alone cannot solve this problem because the inefficiency is built into the algorithm. Even if faster chips are used, the number of required operations still grows at the same rate. This means improvements in hardware are partially cancelled by the increasing workload created by longer inputs. Data centers become larger and more expensive, but performance gains slow down. Companies like Microsoft and Amazon can support large infrastructure, but even they face limits on cost and scaling. This creates pressure to redesign the system instead of continuing to scale it. A signal from leadership confirms that this is not just an academic concern. Sam Altman has stated publicly that the transformer architecture may not remain the dominant architecture. When the leader of a company built on this technology raises that possibility, it reflects internal awareness of the limits. This is not a sudden failure, but a gradual recognition of constraints that are becoming harder to ignore. Engineers inside these organizations are already testing alternatives that aim to reduce compute cost while maintaining performance. The transition is being planned rather than forced by a sudden breakdown. State space models represent one of the most direct attempts to solve the scaling problem. Instead of comparing every token with every other token, these models process sequences in a linear way, where each step depends on the previous state. That means the compute cost increases in proportion to input length rather than increasing quadratically. A model known as Mamba demonstrates this approach by matching the performance of larger transformer models while using fewer resources. The system tracks information as it moves through the sequence instead of storing all pairwise relationships. This reduces memory usage and allows longer inputs to be processed efficiently. Memory-augmented architectures introduce a different solution by allowing the system to store and reuse information across interactions. Instead of restarting from scratch with every prompt, the model maintains internal states that can be updated over time. Research groups at Google DeepMind are exploring systems that modify internal parameters during operation to improve continuity. This allows the model to retain useful information from earlier inputs and apply it later. The observable result is more consistent responses and better handling of long conversations. However, this approach introduces new challenges because uncontrolled updates can reduce stability and accuracy. Mixture of experts models take a different path by reducing unnecessary computation. Instead of activating the entire network for every input, the system selects specific components that are relevant to the task. Each component is trained on certain patterns, and only a subset is used for each token. This reduces the number of active calculations while still maintaining strong performance. Companies such as Mistral AI have deployed this approach to improve efficiency. The routing system that selects which experts to use becomes critical, and errors in routing can reduce accuracy if not managed carefully. Hybrid architectures are emerging as the practical direction because no single approach solves all problems. Engineers are combining transformer layers with state space components and memory modules to balance performance and efficiency. A hybrid system might use attention for short-range relationships and linear processing for long sequences. Memory modules can handle persistent information without overloading the main computation path. This creates a system that is more complex internally but more efficient overall. The added complexity is accepted because it allows the system to scale more effectively. The impact of this shift becomes clear when considering real-world use. More efficient models can handle longer documents, continuous conversations, and larger datasets without excessive cost. This allows AI systems to operate in environments that were previously impractical due to compute limits. Lower compute requirements also reduce the barrier to entry for smaller teams and individual developers. A system that once required a large data center could eventually run on a high-end workstation. This changes who can build advanced AI tools and increases competition across the field. The transition away from pure transformers will not happen instantly because existing systems are deeply integrated into current products. However, the direction is already set by the limitations engineers are encountering in scaling and cost. Research is moving toward architectures that scale more predictably and manage memory more effectively. Over the next few years, hybrid systems will likely become standard in new deployments. Older designs will remain in use, but gradually lose dominance as better alternatives prove themselves. The architecture is evolving because the current approach has reached its limit. Please like and subscribe. Thank you for watching.